Hey guys, welcome back to the AP Physics 1 video series made in conjunction with Prep B. Today we're looking at dynamics. So before we start, make sure that you have previous kinematics knowledge. If you don't, please go back and watch the previous video on kinematics. As always, my name is Alex and I'm working with Ether to bring you guys this content. Let's get started. We'll be going over Newton's first, second, and third laws of motion with practice problems as we go along. Starting with Newton's first law, we have the simple concept of force. Force is a form of energy that is calculated per Newton of energy per meter, a Newton meter. This is also called a joule. Newton's first law takes place in an environment where there is no outside force. Outside forces are things we experience, such as gravity, air resistance, friction, etc. The law states that an object at rest stays at rest, while an object in motion stays in motion. We call this the law of inertia. But how do we make an object move? This question leads us to Newton's second law, where we deal with net force, mass, and acceleration. The second law takes the form of an equation. Force equals mass times acceleration. Force, as in net force. The mass of an object differs from the weight of an object. More on that later. Forces are vectors. Once you label a force as positive, a force from the opposite direction automatically becomes negative. Net force is the sum of all forces. This is very important as we start to apply these laws, but before we get to practice problems, let's talk about Newton's third law. Here, we have weight and gravity. These are two factors that are experienced in real life, and so they're crucial to calculations in dynamics. For example, let's say I have a surface or a table, and an object placed on this table experiences multiple forces. Gravity is always pulling on the object from its center of mass, but it's not falling through the table, just like how you're sitting on a chair right now, but you're not falling through the chair. That's because Newton's second law comes into play with a force we call the normal force. It's the table that exerts this normal force to counteract gravity. If I were to give this object a push, I would exert an applied force. The opposite of applied force is friction, which is equal to the normal force times a coefficient we call mu. It's important to note that normal force and friction force act at a point of contact with the surface, while applied force and gravity, which is the weight, act on the center of mass. So, to further increase your understanding, we're going to do some practice problems right now. With these practice problems, you always need to draw what we call a free body diagram. So I'm going to cut to my other screen, and we're going to work through two practice problems. First question. A block of mass m is accelerated across a rough surface by a force of magnitude capital F that is exerted at an angle theta with the horizontal as shown above. The frictional force on the block exerted by the surface has a magnitude lowercase f. What is the acceleration of the block? Real quick here, we're just going to draw our block. It's on a surface. We have our friction force acting on it, lowercase f, and we have a force of magnitude f pulling at an angle theta to the horizontal. We're looking for acceleration, and we also already know the mass, which means all we need to do is use the F net equals ma equation. Isolate for a, so acceleration equals F net divided by mass, and we just gotta solve for F net. However, we can't just go F minus lowercase f, because this one's at an angle to the horizontal. So first we have to figure out the magnitude of this mass. If we take a vector triangle, a right-angled triangle, with this component being the F force, and this would be our angle theta, we have a new component here, which I will simply call FH, F horizontal. Because if I draw this box right here, I'm not going to draw the surface so that the arrows can show properly. Here's our friction force. But because we know from the question that it's moving in a direction this way, that means this component, this FH, has to be larger than the friction force. So now we just gotta solve for FH, and FH we use our trigonomic ratios. We have SO, CA, TOA, and what we have right now gives us cosine. So F cosine theta equals FH. Now that we have that, then we can just sub it back into the Fnet equation, because Fnet equals FH minus lowercase f. That would give us Fnet equals F cosine theta minus friction. Sub it back into this equation. We have acceleration equals F cosine theta minus friction divided by mass. And that would be choice D for this question. This second question here is, when the frictionless system shown above is accelerated by an applied force of magnitude F, typo right there, the tension in the string between the blocks is, and then we choose. So because it's a frictionless system, there is no opposing force to the applied force. So if I draw that down right now, we don't even need our surface here, actually. We have the applied force here. They just call it F. And there's nothing, no force on this side, non-existent, pulling as the opposite force, which means this force here must be the same magnitude as your applied force. If you think about it, a string, actually, it doesn't really say it's a string, but there's the word tension. You can't have tension unless it's a string. So right now, if you have two objects and the string is slacked, you can put force on the first object, but the second object won't budge until the string is pulled tight. The magnitude of the force that's pulling the string tight is the magnitude of this force. And so, our answer is A. And that will be all for today. Again, if you guys have any questions, you can always hit us up at our Instagrams, and we will see you next time.